I first introduced potential by talking about the difference in how to solve problems. You can solve problems with force, you can solve problems with energy. You can solve problems with the field, which is a force per unit charge. You can solve problems with potential, which is the energy per unit charge. But I don't want to imply that we don't, they're separate things, that we think of them separately. We often think of them together. When you look at an electric field, you might want to be thinking about potential. And when you look at a potential drawing, like I'm going to show you, you want to think about field. Because they are, of course, they are parts of the same thing. So we do look at them together all the time. So let's do that for two of our favorite fields. A charge, a big charge, which we now know acts like a point charge. And these beautiful field lines I love to draw out, 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 out. And I have to draw 8. I don't know why. I think it looks better with 8. We like that field, and we also like this field, the uniform field. Uniform field, like that. And now we know where a uniform field comes from. We must have a big plane of charge right here, creating a uniform field going that way. So there we have our two fields drawn with field lines. So let's think about the potential around these fields with delta V. So delta V equals minus the integral of E dot ds from A to B. That's our definition that we have derived. Minus integral. So first, we can go along a field line. Let's go along this field line. Start here. I'll erase the arrow from this one. We're going along the field line to here. We've walked along that field line. What is delta V if we walk along a field line? Well, ds went this way. E goes that way. This dot product is positive. So delta V is going to be negative. So that means we're going to lower potential when we walk along a field line. If this had been, say, 10 volts, this position in space, say, was 10 volts based on how close you are to this charge and how much charge it has. If you go this way, it's going to go down. Maybe this one is 8 volts. And if you keep going farther away, maybe it goes to 4 volts. And if they set up the problem right, at infinity, it'll be 0 volts, right? Because that's always the zero of potential at infinity. So if you go that way, the field goes down, or the potential goes down because of that negative sign. Because when you go with the field lines, the potential goes down. Which makes sense, because remember, it's potential energy. If you have a positive charge and it goes this way, its potential energy goes down. It gains kinetic energy. The whole story kind of tends to hold together. If it doesn't, we're in deep trouble. Now, what if you walk perpendicular? Okay. So if you go this way, then something different happens. So if you move ds perpendicular to E, delta V equals 0. So this is sort of an interesting thing. So if I go that way, it's also 10 volts. And if I go that way again, it's also 10 volts. And if I go that way again, it's also 10 volts. And the way to move, to keep it always perpendicular to the field lines, is to move in a circle. And if this is a spherical symmetry, the lines are going radially straight out, and I go around a circle, then delta V is always going to be 0, because I'm always going perpendicular to the field lines. I could also do the 8-volt field line, the 8 volts if I wanted, as long as I stay perpendicular to the field lines everywhere I go. I'm going to map out a circle out here at 8 volts. You could go far, less far. You could just go in between. 9 volts is in there somewhere. 9 volts will also have this dotted line. Okay. So these dotted lines, what are they? These are the equipotentials, right? So equipotential means same potential, equal potential. It means basically the constant potential. It's the equipotential but it's not a line, it's a surface. It's the equipotential surface. The field we represent with lines. So you would have to do these in the plane of the board. You could have some coming out of the board, some coming into the board. We think of field in terms of the lines. It's really a flux if you want to think in terms of vector calc, but we think of it as lines. But this surface, these lines, where it's constant, it's actually the, you can go perpendicular to this line in any direction in a plane. Right? So these things I draw as circles are actually spheres. They're equipotential surfaces. They're not lines. In 2D, we draw them as lines all the time, but they're actually spheres. So I think, just make sure you see it, visualization lab. We'll do one of these. So here you can see our red charge and our green field lines emanating from the charge. And this gray sphere represents the equipotential surface. In 2D, we might draw it as a circle because we're just seeing a cross-section of it. Here, you're seeing the whole surface. And if I move it around a little bit, you can see clearly the field lines are going all around from the charge, but everywhere you go, the equipotential is a surface. Because that's due to the symmetry of the problem, that's where the potential is constant. Moving along a sphere, you're always moving perpendicular to the field lines. Nobody does any work, the potential doesn't change. So just keep in mind, equipotential surfaces are surfaces. So there you go in 3D. You can see these are spheres with like little lines shooting through them. Right? Everything's transparent so you can see everything. Okay, so that is how we visualize a potential field, a scalar potential field. Okay? Let's look at another case. Let's look at the uniform field. It's always pointing this way. Here, maybe right here in space, this is what you'd call 10 volts. Okay. Well, if we move perpendicular to that line, if we go down, you're still at 10 volts, still at 10 volts, still at 10 volts, still at 10 volts. Since it's a uniform field to the right, we're staying perpendicular to it at all times. We're always at 10 volts. So that's what we'd call, if we're not being careful, we call that the 10 volt line. Might call it, it should be the 10 volt surface. But when we draw in 2D, often you know they look like lines. And here might be the 9 volt line, and here might be the 8 volt line or surface. Right? So there's your equipotentials. They're just evenly spaced in a uniform field because all you're doing is drawing lines that are perpendicular. And they're actually two-dimensional planes in the plane of the board.